If deadly solar flares bombard a manned spacecraft headed for Mars, the astronauts must remain shielded for as long as it might last. In a small emergency shelter, they could grow weary of both the cramped space and each other. Their resilience would be thoroughly tested.
Frontiers like Mars are vital for people because they give us freedom and they give us challenge. What a frontier does, like the American West, is it throws people into a new situation where they are both free to innovate and forced to innovate because the old ways of doing things no longer work. They're forced to throw off the moss. They're forced to break off the barnacles. They're forced to create something new. And that's when people display really what is best in them. That's when they're most challenged.
Today, there are 6 billion people on this planet. When I was born, there were 2 billion people on this planet. In less than 3 generations, the number of people on this planet has tripled. In the next 2 generations, it's going to double again. That's 12 billion people. These people need resources. That's one of the major reasons we would consider Mars.
Apollo taught us that a manned mission to Mars will be the most difficult psychological challenge any human has ever faced. On Apollo 17, astronaut Gene Cernan was thinking about the risks he was taking throughout the entire journey.
Stand by for touchdown. Stand by. 25 feet. Down at 2. Getting a little dust. Feels good.
There's a lot of excitement, a lot of things going on during the landing, a lot of noise, if you will, dust and things happening.
10 feet. Contact. Stop push. Engine stop.
All of a sudden you get to the point where you touch down and you shut the engine down. At that point, it is perhaps the most quiet moment in the entire life of any human being everywhere, because it stops. The dust stops, the noise stops, the motion stops, and you just sit there and listen for hissing or tanks that are leaking or whatever. There you are in the middle of this magnificent desolation. Should you fall and rip your suit, you're in trouble. And then you get in a car, an electric car, and you drive away from your home on the moon. You drive out of sight. You go over the hill and around the corner. Should the car break down, well, we had rules. You can't go further than you'd have to be able to walk back.
3, 2, 1, ignition. Right away, Houston.
What would happen if that didn't fire? It not only had to fire when you left the surface, it had to burn within the exact length of time, or you wouldn't have made it into orbit. You would have slowly crashed back on the moon. You accepted those kinds of risks. The challenge, the opportunity, maybe some people wouldn't. But I've got to believe most people, given the opportunity, would have accepted the same level of risk that we accepted to go to the moon.
To be part of the effort to first stake out a human presence and actually make it permanent on another world is something that I would sacrifice a lot for. And so the risks involved, if they were weighed and measured and planned against, would be acceptable, just as we accept risk in going into space on the space shuttle. And the same kinds of risks that explorers accepted in the past history of human exploration on Earth would be analogous to those, and I think actually less in the case of going to Mars than we faced hundreds of years ago.
I would certainly like to see all of the various space programs work together with going to Mars as their objectives, because I think that would just be an outstanding thing for the different nations of the Earth together, to work together and toward the common goal of going to Mars. I just think it would be just absolutely marvelous, and I would like to see that happen within my lifetime.
Russia's space station Mir holds the record for flights of long duration. Today, cosmonauts spend up to 14 months in space, twice as long as the trip to Mars and almost half the length of the entire mission. Long stays can be enhanced by some of the comforts of home. Mir has even had a steam bath, where cosmonauts could take a traditional Russian banya complete with a birch branch. But the cosmonauts have learned that over time, things can go wrong, as they did for Vladimir Titov and Musa Maranov during their 13-month mission.
2 months into our flight, we had an orientation problem. The space station drifted out of alignment with the sun, and suddenly we couldn't charge our solar batteries, and so we lost energy. And that was scary because we had to turn off all the lights. The fans stopped. Electricity was low on the ship. We were trying to get out of this situation for a long time, about 3 weeks. We had to restore all the devices that didn't work.
While they could have taken a lifeboat capsule back to Earth, something that wouldn't be possible on a Mars mission, eventually they resolved the crisis. But then a new one arose.
There were moments when we got bored with each other. Mostly, it was the result of psychological stress. We never really fought. Instead, we just went to the porthole and observed the Earth. Did our own thing when we got bored. Fortunately, whenever we had important jobs to do together, all the problems between us would vanish.
How will we select the crew for the first human mission to Mars? People who can handle both the risks and the stress. The answer may lie behind these gates at Russia's cosmonaut training center, Star City. In the United States, psychological factors play a small role in deciding who goes into space. But in Russia, psychology is central. At all the milestones of a cosmonaut's training, someone like psychiatrist Oleg Rumin is there observing. Today, Oleg Kotov is taking his first ride in the centrifuge to see if he can withstand the G-forces of a rocket launch. To test his ability to concentrate under pressure, he's told to press a button every time these lights go on. Oleg will be subjected to nearly 7 Gs. In the control room is the psychiatrist Oleg Rumin.
I'm looking on his expression and behavior reaction, and I'm looking for his eyes. It's viewing just one point or maybe space around him.
The test lasts only 5 minutes. From a physical point of view, Oleg did fine. And from the psychological?
A little bit nervous, but this is the first rotation on a centrifuge for this young cosmonaut. And this is a good person. I like that.
After a solar flare crisis, the crew would regain access to the entire spacecraft. A top priority would be to assess whether electronic systems had been damaged by the radiation. Even though damage to a spacecraft may be minimal, mission planners anticipate stress to astronauts could be heavy. So they have developed ways to ease the tension with messages from loved ones. Because there would not be much room on the spacecraft to include scientific equipment or experiments that weren't specifically for use on Mars, the challenge would be to keep busy. Astronauts could spend hours gazing through the ship's telescope. Others might exercise. But all would be thinking about what lies ahead when they finally land on the red planet. One of Russia's most important psychological tests for choosing cosmonauts takes place in this room. Called the Serta Camera, or silent chamber, potential cosmonauts must spend 10 days here in solitary confinement, going without sleep for the first 3 days. Designed to simulate the stresses of a real mission, all communication with the cosmonaut is made through a series of color-coded lights. His first test is to count numbers. But there's a twist. The numbers are all scrambled, and the candidate must count forward with the black ones and backward with the red. The fewer errors he makes and the faster he counts, the higher his score. But to complicate things even more, a tape of someone else counting is piped into the room at the same time.
8 черные. 18 красные.
Now, the second test. Look at this. Can you remember these symbols? The cosmonaut candidate gets only 2 seconds to look at them, and then he has to write them down from memory. The stress begins to mount. When he gets sleepy, exercise is ordered. For the entire test, this pass-through cabinet is the only contact with the outside world. He's fed the same food cosmonauts eat in space. And as time ticks by, the pressure builds as it would for a cosmonaut on a hectic mission. Every few hours, he's asked to arrange a series of colored cards. According to Russian psychological theory, the order he chooses should reflect his state of mind. As fatigue sets in, he fights sleep, while commands keep coming. He gets slower at doing the tasks, but speed is no longer crucial.
Everyone gets tired, but some just stop working. They don't even struggle with the situation. They give up. Others keep working but make too many mistakes. Another bad reaction to sleep deprivation is hallucinating. If a person has hallucinations during the test, it's a strong sign that he shouldn't become a cosmonaut.
After 3 days of total sleep deprivation and 7 more with just a little sleep, the ordeal is over. For a lengthy Mars mission, stress tests will be the key to choosing the right astronauts. Here in Star City, psychologists also have a test to predict which cosmonauts will best get along with one another. It's called the homeostat, and oddly enough, the idea for it came from the communal showers where cosmonauts used to wash up after training. Psychologists observing the cosmonauts often heard complaints about the water temperature, but only when certain groups were in the shower. The problem, as one person made his shower hotter, everybody else's got colder. Psychologists concluded that if a group of cosmonauts could solve the problem among themselves by adjusting their showers, they were probably compatible. That's the concept behind the homeostat test, only instead of water, it uses an electronic box with a knob and a meter. Getting the needle to 0 is the equivalent of a warm shower. And even if you don't adjust your needle, it moves when your colleagues adjust theirs. At first, each member of the group started out making large movements with their knobs to get the feel of the device. The psychologist watched the drama unfold on a master display panel. Soon, Oleg decided to stop moving his knob, letting Tanya and Valery try to solve the problem first. It's much easier to get to zero when only two people are adjusting their knobs. Once Tanya and Valery hit their targets, Oleg started making small knob movements that the others could adjust to, until at last everyone had a zero. According to the homeostat test, this group would get along fine in space. Aboard Mir, many of the things that crews treasure most on long-duration missions won't be available on a trip to Mars. Distance will prohibit the real-time back-and-forth video conferences with home that cosmonauts enjoy at least once or twice a week. Portholes, which allow the crew to look back on Earth whenever they're homesick, will be useless.
Everyone who flies in space looks out the window, and they do it almost at every opportunity they have. The sights are fantastic. It's not a view that you can get anywhere else.
If you couldn't sleep for some reason, you just go to the window and you could enjoy this Earth view for a very long time. In Mars flight, we will lose this opportunity.
A flight to Mars will be a frozen picture of unmoving stars, and the Earth will be just a dot among them.
A new computer system developed by NASA might help ease the pain by allowing Mars voyagers to take a bit of home with them.
This is when Dan and I were watching the dog, and we had a great time. He splattered soapy water all over us.
The concept was developed for American astronauts orbiting on the Mir, but it could equally be applied to a Mars journey. Before an astronaut leaves Earth, his family and friends would record images, sounds, and messages.
Hi. All right. Say cheese. Hi, Dad. It's really neat that you're in space. I'm really excited, and I can't wait for you to come back.
Back at NASA, they would be loaded into a computer for the family to edit the way they chose.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Dad. Happy birthday to you.
The end result would be a computerized photo album that an astronaut can browse at leisure. If all other communication with home failed, at least an astronaut would have this.
Well, ideally, we'd like to have the family update these with fresh video and fresh still pictures on a monthly basis and transmit those to the vehicle as it's moving to Mars or as it's coming back to Earth. But since transmission technology isn't always 100% reliable, at launch, we would like to have at least one video or still surprise per day of the mission on board that they can take with them.
Mission Control, this is Mars Explorer 1. Hope you're reading us.
Even after 192 days in space, the crew would still be able to communicate with their families.
Your mom had her checkup yesterday and her blood pressure's fine, so stop worrying.
But the time delay would be frustrating. The astronauts would have been drifting in the darkness of space for almost half a year.
How proud you are. Okay, I'm going to pause now, because I know you won't get this for another 20 minutes, and then I have to wait to hear back from you. So I think I'll go work in the garden for a while.
By this time, they would be close enough to Mars to make out some details. 10 more days, and they would be able to set foot on the red planet. A new rocket being developed at Johnson Space Center could end the loneliness of long-distance space travel. It's the idea of inventor and veteran shuttle astronaut Franklin Chang Diaz.
In terms of an astronaut, having flown in space, you become very aware of the solitude of being there and the fact that in a conventional mission to Mars, you're going to spend most of the time looking out the window with nothing really to see. the body is degraded and is severely affected by the conditions of weightlessness. So you would really want to make the trip very fast. And this is very exciting for us because for the first time, we actually are able to make a mission to Mars within 3 months.
Rather than burning gas, this rocket uses electricity to convert gas into a super high-energy state called plasma, which is then propelled out the back at tremendous speed. It won't push a Mars spacecraft any harder, but it would consume much less fuel, so it could operate longer than a conventional rocket and gradually gain more speed.
Okay, ready for the voltage adjustment, step number 3. A conventional rocket essentially pushes the rocket in a one shot by firing the engine until the fuel is completely depleted. The rocket really coasts most of the trip to Mars. Okay, we have 2 red indicators on the microwave. In our rocket, we can increase the speed by maybe factors of 5 or 7, and that is because we are accelerating all the time. And in fact, to travel to Mars, the rocket is always turned on. All right, step number 10 there, Laura. Air heat exchanger water valve open.
A Mars spacecraft using plasma rockets would need 3 small nuclear electric generators to make the plasma. Ironically, back in the 1960s, NASA developed another rocket that used nuclear energy called NERVA. It also didn't burn gas, but heated it to a very high temperature inside a nuclear reactor. In a series of tests, the rocket proved to be very efficient and lightweight, but the concept was ultimately abandoned because of public concern over nuclear power. NASA's plasma rocket would be impossible without nuclear electricity. So if we want to get to Mars quickly, going nuclear is the only way.
Start button to push. There you go.
Today's test is at low power to be sure all the components are working.
Okay, we're almost there. You're going to be ready, right? And go ahead and fire.
Here it goes.
There it is. You can see the discharge. You got a discharge.
The purple glow of plasma gives Chang Diaz confidence his rocket will be up and running by the year 2005, in time to go to Mars. Lessons learned from Russia's space station could also benefit the mission to Mars. American astronaut Norman Thagard's 4 months on Mir proved that cultural and language differences could be a small but irritating problem.
I had already had a couple of years under my belt at that point of Russian language training, and I understood almost everything that they would say. I think I probably had more difficulty expressing myself precisely sometimes, so I didn't try things like jokes. I just always was mindful that if you blow a joke, you can wind up saying something you never intended to say. Gennady, on the other hand, constantly regaled me with jokes in Russian, and a lot of them I understood, and a lot of them I didn't understand. The one instance where culture really was a factor, we found out on board that Volodya, our commander's mother, had died. And I didn't know what the proper way was for Russians to react to a friend to whom that had happened. And what I had to do in that case is just watch Gennady and see how he behaved toward Volodya and emulate Gennady.
To overcome the problem, NASA holds cultural training classes to prepare astronauts, as well as behind-the-scene personnel, for the new era of international missions.
Nice to meet you.
Здравствуйте. Sergei Nikolaevich Demonov.
Walter Barnett, how are you doing?
One of the techniques used is role-playing.
So you're an engineer with NASA?
The lesson here is about conflicting ideas of personal and private space.
Let me show you a picture of my wife, Sasha, and my son, Yuri.
Yeah.
And this is Marina, my daughter. Yeah. Where do you live, Walter?
Well, I actually live right over here in Nassau Bay.
How much do you make at NASA? How much money, your salary?
Well, I guess we get by, but I'd rather not. I mean, that's something I really don't want to discuss. So.
The hope is that by making people aware of the customs and expectations of others, cultural conflicts can be avoided.
You're looking great. You're looking great.
Yeah, thank you. You look good too. It's good to be back here in the United States.
After about 202 days, the Mars spacecraft would reach its destination and gravity would draw it into orbit. The captain would begin a last-minute virtual reality session to rehearse for the landing. He would have been practicing throughout the mission to be sure the descent to Mars would go smoothly. The Martian surface must be monitored closely for violent dust storms that can appear with little notice. Such a storm destroyed an unmanned Russian spacecraft that landed on Mars in the 1970s. From Mars orbit, the crew could also see the specific places they've come here to explore. Places where previous robotic missions detected minerals that might lead to evidence of Martian life, and to crucial underground supplies of water.
Mars has water. There's oceans of water frozen into the Martian soil as permafrost, enough that if the planet was flattened out and the water was melted out of the soil, the planet would be under 600 feet of water. Now that's dry compared to the Earth. If the Earth was flat, we'd be under 6,000 feet of water. But the Earth's a water world. You got rid of the Earth's oceans and froze the rest of the water into the soil, the Earth would be about as wet as Mars.
With just 36 hours to go until the touchdown on Mars, a crew would exercise harder than ever. After 6 months of weightlessness, they would soon have to cope with gravity again. And moving around on the surface in a spacesuit would not be easy.
Man, it didn't feel like this stuff was that hard.
One of the most crucial technologies still lacking today for a Mars mission is a practical spacesuit. Apollo moon suits were little more than inflexible pressurized bags, adequate for life support but awkward for getting around. The Mark III spacesuit, designed and built at Johnson Space Center in Houston, is a major improvement. It was intended for zero-gravity work on the space station, so it's probably too heavy for Mars. But it demonstrates how putting dozens of airtight joints around the suit lets a person bend and move in a natural manner, while still getting the protection of a pressurized shell. The first steps for designing a Mars suit have already been taken in this water tank at the NASA Ames Research Center. Because people naturally float in water, to simulate Martian gravity, research subjects wear a series of weights distributed all around their bodies.
Okay, are you ready to exit onto Mars?
Martian gravity is 39% of the gravity we have on Earth, so a 150-pound man would weigh only about 60 pounds on Mars. He would also fall more slowly when he jumped up and down, but not this slowly.
Why don't you add about 4 in the front, and then add about 2 in the back, and then...
Bruce Webben is director of the spacesuit program here, and he's realized that his subject Eric needs a few more weights. Eric should now feel as heavy as if he were on Mars.
Okay, power's on. Motor's on.
Part of what Bruce Webben wants to know is how far a person's joints bend when he walks in Martian gravity. This will determine how flexible a Mars spacesuit must be to allow natural movement.
We're at 1 mile an hour now. We're going to go up to 3 miles an hour, okay? Okay, 3.
Webben also wants to know how much less energy it would take to walk in the lower gravity of Mars compared to on Earth.
As you decrease the gravity, it makes sense that the effort to move would probably be less. But if you go all the way to zero gravity, then you can't walk. It's a completely different means of locomotion. And so the real interesting questions are what happens in between, and so we need to learn what sort of effort it takes to move and walk on Mars.
While the research subject exercises, Webben measures the carbon dioxide he produces, one way of gauging the expenditure of energy. This will determine how big an air tank astronauts will need to do a day's work on Mars, and how much air conditioning they'll need to stay cool.
This kind of research isn't done then what would typically happen as an engineer, you would over-design. So you would always design the system to be safe, but it would be much larger, the life support system would be much larger than it really needs to be, and the suit would not be optimized at all.
To perfect the design of a Mars spacesuit, Webben hangs weights at various places on a backpack frame. This will help determine the best place to concentrate the mass of the life support system, as well as where astronauts should carry things like tools or geological samples collected in the field. Each time the weights are moved, Webben measures how that affects the subject's balance, comfort, and energy consumption.
Eventually, we'll learn how to distribute the mass of the life support system. It won't necessarily be a backpack. It might be that it's more efficient to have the life support components distributed around the body, some of them in front, some of them in back.
Webben says he could build an ideal Mars suit in just 3 or 4 more years, but further work has now been put on hold by NASA. The crew must land their spacecraft near their return ship that arrived on Mars 2 years ago. By this time, it would have made the fuel needed to get
10
home.
seconds to deorbit burn. Enable engines.
Engine enable.
Burn beginning.
Thrusters would reorient the craft to begin the descent to Mars.
Making contact with Mars atmosphere.
G level. 0.75 Gs. Velocity.
2,000 meters per second. 1,700 meters per second.
1.9 Gs.
1,300
Their
meters
speed
per
would
second.
drop rapidly, and the G levels would climb as the spacecraft's huge aerobrake would produce friction with the Martian atmosphere.
600 meters per second.
Picking up signal from return vehicle.
1.9
And locked onto target.
Ready to deploy main parachute. 5, 4, 3, 2, 1. Begin terminal descent burn.
200 feet.
80 feet. 40 feet. 25 feet. 10 feet. We're down.
Mission control, Explorer 1 has landed.
We have long dreamed about setting foot on Mars.
This is the proudest day of my life.
Television pictures would arrive back on Earth 20 minutes later.
It feels really strange walking, doesn't it?
The landscape has a similarity to the scenery back home. And the water-eroded hills suggest that Mars has a captivating story to tell. Almost 4 billion years ago, Mars and Earth were nearly twins. Both were warm and wet. But for reasons unknown, Mars rapidly became cold and dry. The Explorer 1 crew would land in one of the great river valleys where water was abundant during Mars' warmer days. A manned mission would hope to learn whether life got a foothold on Mars before conditions became so extreme, and whether life still exists beneath the surface today. But the crew's first priority would be to confirm that the return spacecraft that fueled itself from the Martian atmosphere was still in good shape for their journey home. They would also set up a series of weather stations to avoid being caught off guard by a Martian windstorm, which can gust up to 80 miles an hour. Only then would astronauts drill into the frozen floor of an ancient riverbed, searching for minerals, water, and evidence of life.
The possibility of finding some ancient form of fossilized life or some anaerobic life, that is, life that doesn't depend on oxygen living under the land on Mars, would be stunning. Because on this planet, we've all looked up at the sky and wondered, are we alone? Are we unique? Is life unique of any form, however complex or lowly, carbon-based or not? Is life unique to planet Earth?
One of the best places to search for evidence of past life will be in ancient Martian hot springs. On Earth, in places like Yellowstone National Park, hot springs are teeming with microscopic single-celled life. Evidence suggests that life on Earth began in this kind of hot and wet environment. Images sent back by Viking revealed abundant hot springs on Mars billions of years ago, when the planet was wetter and warmer than it is now. So there is a good chance Martian hot springs developed life too. But for NASA paleontologist Jack Farmer, there's something even more compelling about hot springs. Unlike other water environments that might have been on Mars, hot springs almost always leave good fossils of the organisms that lived there, and you don't need a microscope to see them.
Here on the edge of this hot spring, we have a place where microorganisms, bacteria, are being turned to fossils before our very eyes, the kind of fossils we'd like to look for on Mars. The orange areas out here are actually communities of bacteria, and you can see the interesting textures and structures that they produce as they grow upward toward the light. In general, the microorganisms thrive in these scalding hot waters, but the waters are also loaded with dissolved minerals, and as the water cools, particularly in shallow areas, the minerals come out of solution and coat the organisms and entomb them while they're still alive, producing sort of mummies, if you will.
A few feet away from the spring, an entire colony of bacteria coated with minerals has dried up and turned to stone. The structures and patterns visible to the naked eye could endure for billions of years.
We need to go back to Mars, and we need to look for these kinds of places, because these are the environments where that fossil record is likely to be preserved, and this will help us answer the question about life on Mars.
While ancient hot springs might be the best place to look for life, Farmer has also been collecting samples of large fossils that form in lakes and streams. All have unmistakable patterns that a paleontologist couldn't miss if he were actually walking around on the Martian surface.
I think we have good geological evidence of the right kinds of places to go to look for a fossil record of life. We're going to have a lot more evidence as upcoming missions unfold. But right now I feel pretty confident, even based on Viking data alone, that we've targeted some important sites.
If there was life on Mars, how long did it survive as Mars evolved into a frigid and dry planet? The answer may lie in the Canadian Arctic, 400 miles from the North Pole. One of the original members of the Mars Underground is NASA scientist Chris McKay.
Sandstone formations are a couple hundred meters high here.
There is a rock outcrop I would like to explore more.
Along with biologist Imre Friedman, McKay has come here to see what life on Mars might look like in a bitterly cold environment. The Arctic is similar to what Mars would have been like when its climate became borderline for supporting life.
This place is a cold desert. The mean annual temperature is well below freezing. There's thick permafrost underneath us. But more importantly, this area is very dry. In fact, the light snow we see around could be considered a heavy snow for this area. The question we're asking is, can life survive here? Is it possible for life to adapt to these cold, dry conditions?
Okay, let's go and we will see.
Careful here, the snow is slippery. Watch your footing.
Not easy going.
If there is life here, it's fragile and hard to find. If it exists, it's hidden beneath the surface, out of sight. After hours of hiking without seeing a sign, McKay and his colleagues arrive at a spectacular sandstone formation.
Let's go over this one here.
Inside the rock, there is a surprise.
Look at this.
Oh, that's it. That's what we are looking for. The same
A black and green band of algae is just 1/10 of an inch beneath the surface. Here in the Arctic, simple organisms were thriving inside rocks at a depth where sunlight could still penetrate to provide energy and where water would be stored in the pores of the rock.
The amazing thing is that this rock, if you were to look at it from the surface, would show no signs of life, no evidence of the living systems inside it. And yet it provides an excellent example of how life can grow in a very cold, very dry place. A cold desert like here, and a cold desert like on Mars.
Today on Mars, it's probably too cold and dry to find such organisms still alive. Only their fossil remains could still be found. But could life still thrive in some other environment?
all green inside.
Okay, let's bag it.
One of the best prospects of finding living microorganisms on Mars is Martian permafrost. Permafrost is frozen soil.
At the South Pole, a team of scientists drilling in the ice hit frozen water a foot beneath the surface containing a colony of living bacteria. If a subterranean world of microorganisms lurks below the surface of Mars, could larger life forms have existed there too?
If we compare Mars's history with Earth's history, we would expect that nothing more complicated than microorganisms evolved. But there may be reasons to think that maybe Mars went more quickly in its evolutionary trajectory than the Earth did. And maybe it's possible that Mars developed larger organisms on timescales that are shorter compared to how long it took to Earth. Mars is a smaller planet. It may have evolved faster. It may have built up oxygen in its atmosphere more rapidly. Who knows? These are all speculations. But how do we test these speculations? Of course, by going to Mars and looking for fossils.
A crew would be on Mars for a year and a half conducting field work.
We can be there in 2 hours.
For safety's sake, they travel in pairs. They would explore the bottom of ancient lakes where canyon walls slice through millions of years of Martian history, and with luck, they'll reveal some evidence of past life.
Nothing over here.
Paleontologists often go to great lengths to reach the best spots for fossils back on Earth. And on Mars, it won't be any different. Accidents could occur. People might even die. But that's the kind of risk humans have always taken to explore the unknown. But all the risk it took to get there might pay off in spectacular fashion. Within a rock like this, could there be unmistakable evidence that columns of bacteria-like creatures once lived on Mars? If so, our understanding of the universe will never be the same. With each new day, there would be new discoveries to make, new possibilities to explore. Mars experts believe the crew could locate underground ice that could be melted for water. This investigation might change the future of Mars, a dream held both by science fiction writers and by scientists. NASA's Chris McKay believes that we could make the red planet's climate suitable for life through a process called terraforming.
The word means, obviously, to make it like Earth, terraforming. Fundamentally, what Mars lacks is a greenhouse effect. Like the panes of glass in this greenhouse, the carbon dioxide and water in an atmosphere hold the solar energy in and keep a planet warm. Mars's thin atmosphere is essentially equivalent to no greenhouse at all. The first thing we need to do is give it a thicker atmosphere or somehow augment its greenhouse effect. That greenhouse effect would allow temperatures to rise, water to flow, and then life could be introduced on Mars and then life could survive.
In his lab at NASA Ames Research Center, McKay conducted a feasibility experiment to look at one possible way for increasing the amount of Martian greenhouse gases. The basic question was whether soil could be the source for adding more carbon dioxide to the atmosphere.
We think that at one time Mars had a thick carbon dioxide atmosphere, and that as the planet cooled, that carbon dioxide absorbed into the soil, the way water is absorbed into a sponge. And we think that if we warm up the planet, that carbon dioxide will come back out, reforming a thick, warm atmosphere.
In his experiment, McKay simulates what would have happened to Martian soil as the planet got cold. First, he exposes some soil to an endless supply of carbon dioxide gas. Then he chills the soil to below zero temperatures. After a few days, McKay shut off the gas, took away the cold, and measured how much carbon dioxide came out of the soil as it warmed up again. A mass spectrometer revealed the amount was huge. But the machine indicated that for Martian soil to release carbon dioxide, the temperature would have to go up 40 degrees centigrade from its current temperature of 80 below zero.
If we take what we're currently doing on Earth, releasing into the atmosphere greenhouse gases and super greenhouse gases like CFCs, and do the same thing on Mars and continue doing it, in fact, we could easily get a warming of 40 degrees. That kind of change, of course, would be a disaster here on Earth, but on Mars, it would be just what the doctor ordered.
To begin terraforming, Chris McKay proposes that we deploy factories on Mars to produce potent greenhouse gases. As these accumulate in the air, Mars' greenhouse effect would increase dramatically. More solar energy would get trapped in the atmosphere, the temperature would rise, and perhaps in 100 years, carbon dioxide would start coming out of the soil, releasing another potent greenhouse gas into the atmosphere and raising the temperature. Soon, during the Martian summer, water would melt at the poles. And as some of this water evaporated, another powerful greenhouse gas, water vapor, would enter the atmosphere. The temperature would be high enough to sustain water year-round, and Mars would become a much more Earth-like place.
This is the sort of thing that humans are going to be able to do on Mars. We're going to be able to turn Mars into a living planet, okay? And so that while the first settlers on Mars will live in tuna cans, and 100 years later they'll live in domes, a few millennia from now they'll live out in the open, on open grassland and pineland, on a human-transformed Mars.
I think life is a good thing, and I think spreading life from Earth to other locales in our solar system and beyond is a positive thing.
The Mars of today is hostile to life, lacking any liquid water on the surface, and colder even in the summer than the coldest it ever gets on Earth. But during the first human mission to Mars, the crew would conduct an important terraforming experiment to test whether the Martian climate can be changed. By constructing a greenhouse that traps heat from the sun, they would find out whether raising the temperature forces carbon dioxide, a greenhouse gas, to come out of the soil, as Chris McKay predicts. After a few days, they would return to the greenhouse to measure how much carbon dioxide has accumulated. If the increase is large, it would suggest that terraforming Mars, making it Earth-like, could really happen. Once humans have set foot on the red planet, dreams can start to become reality. But which dreams will we fulfill? Will we construct settlements here? Will Mars become an extension of the world we live in today?
I think 200, 300, 400 years into the future, we'll have a civilization from Earth that inhabits Mars, and we will have youngsters, second-generation Martians, who will say, hey, my grandmother and grandfather back in the umpteenth century came from Earth, and it will be a relationship, Earth-Mars relationship, very much like an old country, new world relationship we have seen in the past 3 or 4 centuries.
If we do set up a human civilization on Mars, that will create the incentive for further advances in interplanetary transportation. Just as Columbus ventured the Atlantic in 3 ships that were really designed for the Mediterranean, and that no one in their right mind, even a century later, would have attempted an Atlantic crossing with. But once people found out there was something to go to across the Atlantic, once they made something worth going to across the Atlantic, that became an incentive for the advance of naval architecture. So we went from those carracks to clipper ships, to steamships, to Boeing 747s. Now, the same will ultimately be true with Mars.
It has always been our nature to dream the impossible. Soon, we can send the first human explorers to the surface of Mars, safely and economically, using technology that's almost ready today. Getting humans to the Red Planet could finally answer many of our long-held questions. Why did Mars become so cold and dry? How much water is left on the planet? Was there ever life on Mars? Is there any life there now? And there will surely be more surprises, discoveries we can't even imagine, just waiting at Destination Mars.